Okay, we're in section 16.3, potentials and charged conductors. Let's share the PowerPoint and let's get started. All right, from the work equation, we see that the work done on a charge by electric forces is related to the change in electric potential energy of the charge. That's the work equals minus delta PE, potential energy. From the potential energy equation, we see that the change in electric potential energy between 2 points A and B is related to the potential difference between those points. Let's combine these two equations. Notice that this means no net work is required to move a charge between 2 points that are at the same electric potential. In mathematical terms, this result says that W equals 0 whenever VB equals VA, in which VB minus VA, they're the same, equals 0. Okay. Remember when we talked about a conductor is in electrostatic equilibrium in the last topic? You learned that a net charge placed on a conductor is entirely on its surface. Also, we showed that the electric field just outside the surface of a charged conductor in electrostatic equilibrium is perpendicular to the surface, and that the field inside the conductor is 0. Now let's show that all points on the surface of a charged conductor in electrostatic equilibrium are at the same potential. Take a look at the figure here. The black line connects points A and B on a charged conductor. We can assume the charges on the conductor are in equilibrium with each other, so none are moving. In this case, the electric field is always perpendicular to the displacement along this path. This has to be the case, or part of the electric field tangent to the surface would move the charges. Because E is perpendicular to the path, no work is done by the electric field if a charge is moved between the given 2 points. From our equation of the work equals minus Q VB minus VA, you can see that if the work done is 0, the difference in electric potential is also 0. That means the electric potential is a constant everywhere on the surface of a charged conductor in equilibrium. Since the electric field inside a conductor is 0, no work is required to move a charge between 2 points inside the conductor. Our equation tells us that if the work done is 0, the difference in electric potential between any 2 points inside a conductor must also be 0. We can conclude that the electric potential is constant everywhere inside a conductor, and since one of the points inside the conductor could be arbitrarily close to the surface, we can say that the electric potential is constant everywhere inside a conductor and equal to the same value at the surface. So what this tells us is that no work is required to move a charge from the interior of a charged conductor to its surface. Keep in mind, though, that the potential inside a conductor is not necessarily 0, even though the interior electric field is 0. Okay, the electron volt. Now is a good time to introduce a new unit, an energy unit which is commonly used in atomic and nuclear physics is the electron volt, the EV. For example, electrons in normal atoms typically have energies of tens of EVs. Excited electrons in atoms emitting X-rays have energies of thousands of EVs. And high-energy gamma rays, electromagnetic waves emitted by the nucleus, have energies of millions of EVs. The electron volt is defined as the kinetic energy that an electron gains when accelerated through a potential difference of 1 volt. Let's remember that. The electron volt is defined as the kinetic energy that an electron gains when accelerated through a potential difference of 1 volt. Equipotential surfaces. An equipotential surface is a surface where the potential is the same at all points, which means the potential difference between any 2 points on an equipotential surface is 0. So no work is required to move a charge at constant speed in an equipotential surface. Also, the electric field at every point of an equipotential surface is perpendicular to the surface. If the electric field had a component parallel to the surface, that component would produce an electric force on a charge placed on the surface, which would do work on the charge as it moved from one point to another. This is in contradiction to the definition of an equipotential surface. We can represent equipotential surfaces by drawing equipotential contours, which are two-dimensional views of the intersections of the equipotential surfaces with the plane of the drawing, like in the figure shown here. We generally refer to equipotential contours simply as equipotentials. In the figures, notice that the equipotentials shown in blue are perpendicular to the electric fields, which are shown in orange. Our relationship for the potential of a single point charge shows us that the potential is constant on any surface in which R is constant. That means the equipotentials of a point charge are a family of spheres centered on the point charges. You can see in the figure on the left. The figure on the right shows the equipotentials associated with two charges of equal magnitudes but opposite in sign. That ends this section. We're going to skip the next section, 16.4 applications. You're welcome to review it if you're interested, but I won't test you on any of the information held in it. The next section we'll cover is 16.5 capacitors.